Good morning, good afternoon, good evening to everybody. So welcome back again to the Coastal Resilience Talks, the webinar series organized by the Decade Collaborative Center for Coastal Resilience, CMCC in Italy, and Deltares in the Netherlands. The Decade Collaborative Center is one of the actions of the decade that focus on the decade challenge, increase community resilience to ocean and coastal risks, and that plans to have outcomes to a safe ocean. Please, next. Our partner alliance network is composed of Deltares, as I said, from the Netherlands, University of Bologna, that hosts the Decade Center, Collaborative Center for Coastal Resilience. Heron, very happy, the last entrance of the Coastal Center, Helmholtz Center in Germany, and CMCC in Italy. Next one, please. Today, I'm very happy and honored to have to talk about Trinidad and Tobago, oceanography, and coastal protection. And our speaker is Salomi Seeram, working at the Coastal Dynamics Limited in Trinidad and Tobago. She is one of the examples of young people who have undertaken a career in an essential field that is from private for coastal community resilience. That's very important. And her background is in numerical modeling, geospatial analysis, and climate change. And she is working also with satellite data, developing web portals, everything that really is needed for coastal resilience. So thank you so much, Salomi, for coming with us. Last information before I give you the floor, Salomi, is the question and answer session. So we will not allow people to directly address the speaker, but people are allowed to put their question in the session. You will find at the bottom of the page a button where you have dots and you find more, you get in more, you can access the Q&A window. And please put your questions that will be answered sequentially at the end of the talk. Please note that the seminar is recorded, and by participating, you consent to the recording and its future use for education and promotional purposes to be used. And so with that, I completed and leave the floor to Salomi. Thank you.
Yeah, let me share. Just confirming that you can see my screen.
Yes, we can.
Okay, good. So, hi everyone. Thank you, Nadia, for the kind introduction. And thank you to the Center and its network for the opportunity to be a part of the climate resilience talks. So as Nadia mentioned, today I'll be talking about some numerical models, particularly hydrodynamic and spectral wave, that Coastal Dynamics has developed to represent the ocean environment around Trinidad and Tobago and the Eastern Caribbean. So who is Coastal Dynamics? We are a multidisciplinary environmental consultancy based in Trinidad and Tobago, and we actually celebrated our 30th anniversary last week. We're a company of about 46 to 50 people with varying expertise, like myself. So my academic background stems from environmental sciences, marine sciences, and geoinformatics. And we have conducted and I am a coastal scientist at Coastal Dynamics, and we have conducted projects throughout Latin America and the Caribbean region. Our services include like environmental impact assessments, shoreline monitoring, greenhouse gas inventories, surveys which include wave and current meter deployments, water and sediment chemistry, beach profiling, drone surveys for aerial imagery or LiDAR, as well as benthic assessments. And just wanted to start with what is numerical modeling. It's just a method of representing the physical processes on it through mathematical equations. There are a few equations you can see on your right, but you can imagine a coastline. We want to represent this area in both space and time. So we can represent the area through a mesh or grill where we split up into tiny little grid cells, and through time steps to see how the environment would move. So we use computers to solve these mathematical schemes or numerical schemes for each grid cell and each time step using iterative processes. And it allows us to represent the environment virtually and run what-if scenarios of how the environment will behave. So, for example, the same coastline, how much would be flooded in a major hurricane? Or what wave height could possibly breach a potential seawall design? So those kinds of things. And so for us, small island developing states in the Caribbean are heavily dependent on the marine resources. And in the case of Trinidad and Tobago, this is no different. We are heavily dependent for our oil and gas, fisheries, and tourism industries. The currents and waves affect navigation. It affects pollution trajectories, shoreline stability, as well as overall ecosystem health, including mangroves, coral reefs, and other like mudflats. And so understanding the oceanographic conditions is very important for managing the resources, conducting maritime operations in a safe way, developing effective response strategies in case of oil spills, and overall coastal zone management. In case of Trinidad, our measured long-term wave and current data set is a bit of a data gap, and as such, these models can act as a way to bridge these gaps and also help in the understanding of waves, currents, and water levels, how they change through space and time for the islands. So where is Trinidad and Tobago? So we are located in the Caribbean, and we are the southernmost twin island state, as you can see when we zoom into the bottom right here. And our east coast borders the Atlantic Ocean, the west coast borders the Gulf of Paria with Venezuela, and the Gulf of Paria is a semi-enclosed basin, and Tobago lies near the continental shelf edge within the Caribbean. Our environment is heavily influenced by freshwater runoff from the Orinoco and Amazon rivers, and is also impacted by the Guyana currents, North Brazil currents, the swells propagating from North Atlantic, the trade winds, and also seasonal tropical cyclones. So how did we develop the models? In collaboration with the DHI group, a three-dimensional hydrodynamic model for currents and a two-dimensional spectral wave model were developed using DHI's Mike 21 and Mike 3 suite of products. And high quality boundary conditions were used to run the models to, one, provide improved forecasts data for the Eastern Caribbean for up to 5 to 7 days, and also to understand the oceanographic conditions, particularly around Trinidad and Tobago. The 3D model, the HD model, hydrodynamic, I'll refer to it as HD. So that HD model, our domain extended from Martinique to the north, which you can see here, to the Orinoco Delta in Orinoco Delta, Venezuela, in southeast. And the model was developed in 2012 using a flexible mesh. And that just means that there's various grid sizes within this domain. So in our case, it's about 11 kilometers for an element side in the offshore area to around 5 kilometers covering the islands. And our model domain had 4 open boundaries, where we had data sets inputted from various sources such as current velocities and density variation from Copernicus, tidal constituents from DHI, and met conditions from NOAA Global Forecast System. The met conditions were across the whole domain, while the boundaries were along the boundary lines. There were also incorporation of discharge rates from the Orinoco system that was also inputted in the model, and it gave us a full water column profile of current speed and direction throughout. And usually for reporting purposes, we don't present all, but we don't present on surface, mid-level, and near-bed profiles. And in terms of the wave model, this was developed in 2017 using the Mach 21. And our domain is much larger, as is a two-dimensional. It covers Angola to the north and French Guyana to the southeast. The element size for the deepest offshore areas are around 60 kilometers, with around this here. And then the nearshore areas, we've reduced it to 2 kilometers for the length to the side. And in this case, there are 3 open boundaries where the inputs were winds from NOAA Global Forecast System and wave boundaries from DHI's model. The model was simulated the growth, decay, and transmission of the wind-generated waves, as well as swells in the offshore and the coastal areas. Our outputs had the surface wave speeds, wind direction, sorry, not wave speeds, wave heights, wave direction, and wave periods. And like with all models, a crucial part of development is calibration and validation. So in this case, this was done at multiple locations throughout Trinidad and Tobago and in the Caribbean, wherever we had data, where conductivity, temperature, depth, CTD profiles, and also wave and current data sets were collected from either deployed ADCPs, which is acoustic dipole current profilers, or any other sort of wave and current. ADCP is just one of the names. In addition to the ones that we've collected, we also incorporated NOAA's national data buoys. So 2 of their data buoys, particularly these 2 here, were used to test the wave model. And these are more offshore buoys. And the calibration and validation procedures were conducted over several years in a iterative or cyclic approach. And we evaluated it through statistical analysis with performance measures, such that how the model performs or the accuracy of the outputs can be assessed quantitatively, yeah. And the like different error matrices were used, like mean error, root mean square error, where the lower the value, the better the accuracy or the fit. Additionally, we also use index of agreement, where it helps indicate model predictive capability. And in terms of index agreement, values closer to 1 is better. So the calibration was done in a cyclic pattern to tweak the parameters to continuously improve the model results until the model was fit for purpose, and we agreed with how it was performing. And then validation was performed with a received set of data, specifically measured data, that wouldn't use any calibration procedure. And here's just locations all throughout. So we have offshore, we have nearshore throughout Trinidad and Tobago. So this is just some results from the validation, and the measured versus modeled is QQ plots, so it's quantile plots. Overall, the hydrodynamic model may have underestimated some of the velocities at the higher end of distribution, and may have overestimated at the lower end. Like for the North Coast, it showed this pattern for surface and mid depths during wet season. While Tobago leeward coast had a little overestimation at the near depth in the north-south direction, similarly during the wet season. But the mid-range current speeds were better represented, and the metrics for the errors show that it was less than 0.3 meters per second during dry season, less than 0.4 during the wet season, while the index of agreement range between 0.5 to up to 0.97 for dry and up to 0.9 for the wet. However, overall, based on the stats and the graphs, the model performed well, as we had to do a balance. We had to strike a balance between the high resolution and accuracy versus how much resources that these models would demand in terms of computational. As the HD model is a full 3D model over a big domain. Yes, we did this for the larger model, but all of these reflect that grid or that domain. But as we get projects, or as we have particular requirements, we do refine the domain to make it more accurate for certain areas. Similarly, for the waves, we also did some from quantile plots. In this case, it's for significant wave height, and this model tend to have a better fit across all the coastal areas, with corresponding error values being less than 0.2 meters for both dry and wet season. And index of agreement is ranging between 0.7 to 0.9 meters for both seasons as well. And this generally indicated a strong model performance. This is a 2D model, so the computational demand and the boundary inputs compared to the hydrodynamic model are less intensive and complex, and the waves tend to perform better across the domain. So what did we see? We saw that the hydrodynamic model was able to replicate the intricate circulation patterns in your area, capturing the North Brazil rings, as you can see on the right, which are large anticyclonic rings that result in particularly extreme currents off the East Coast, with increased current speed and directional changes over a few days. It also captured the Guyana currents, and as well as the circulation within the semi-enclosed Gulf of Paria, which you can see better in here. So the Guyana current comes from the north, from southeast, so it flows to the southwest, so it flows to the northwest, and then it splits into two streams. So there's one stream that flows westward here into the Columbus Channel and then into the Gulf of Paria via the Serpent's Mouth. And within the Gulf of Paria, we have a clockwise gyre occurring, and the northward stream. So coming through here, it is like around 1 meter per second to 1.5 meter per second. And then as it leaves here, it reduces to about 0.8 and flows. This here is Dragon's Mouth, so it flows through here into the Caribbean Sea. The other stream, which is the outer stream, travels along the east coast of Trinidad through the Galleon's Passage, and which is around here, and then into the Caribbean Sea. It also kind of subdivides again when it reaches Tobago, where it is south coast. It divides to one towards the northeast side, which is on this way, and then one northwestward through here. And Tobago around here usually reaches up to about 2 meters per second. That's the hydrodynamic. In terms of the wave model, it captures the wave environment very well in terms of patterns, with the higher waves being observed along the windward coast due to the prevailing trade winds. To be a little bit more specific, along the east coast of Trinidad, we have waves predominantly from east and northeast due to trade winds. The wave heights, significant wave heights, can vary from as little as 0.1 meters in the nearshore area to around 2 meters in the offshore. In terms of south coast, we have lower energy compared to the east, where we have 1 meter from the southeast direction. And in terms of the Gulf of Paria, it's very low energy wind waves and swells due to limited fetch. And this just means that the area in the Gulf of Paria kind of limits the generation of the wind waves. To the north of the Gulf of Paria, waves also are refracted and diffracted through Dragon's Mouth and propagate southward into the Gulf of Paria. In terms of Tobago, the windward coast, the waves coming from east and northeast due to trade winds as well, and similar to east is up to 2 meters offshore for the wave height. And for the leeward side of the Tobago, it's a lower wave energy with the wave heights averaging less than 1 meter offshore and up to about like 0.5 nearshore in the coral protected areas. Right. And so we have a lot of applications that could be used for these models, especially because our region is dependent on the marine resources. So I'll just highlight a few. So like for the oil and gas sector, the models are critical for like operational planning and safety. Operators can use forecasts to schedule the offshore activities efficiently, minimizing the downtime between rough sea conditions, and also supporting HSE, health, safety, and environmental decision-making activities. Long-term data sets for wave and current statistics would also be essential for engineering designs of offshore platforms, subsea infrastructure, and future marine installations. In terms of port and maritime operations, the models help port managers for navigation safety, vessel rescheduling, dredging operations, cargo handling efficiency. This is particularly important for during wet season and when we have strong weather systems affecting the Caribbean Sea or Atlantic, in our case, Atlantic Ocean. And it could also be used for disaster preparedness and climate resilience, where We can use it to support storm surge forecasting, coastal flooding assessments, and emergency response planning during tropical cyclones. And as climate change is making everything worse, it's increasing the risk of coastal hazards, sea levels rising. These tools are even more important for the long-term adaptation planning and resilience strategies. For coastal engineers and shoreline managers, the models can help evaluate shore erosion areas, sediment transport, and shoreline change to support design of coastal protection structures and for future coastal development. I think the last example would be the benefits to recreational tourism users. So it can help the safety and also being able to manage the tourism activities. For examples, surfers knowing which days will have like high wave energy for surfing, or days when beachgoers are want to be particularly careful if there are certain high currents or waves at beaches that can impact their safety while enjoying the beach. We could go in further. So as Trinidad and Tobago is heavily dependent on the oil and gas industry right now, and because of that, is also exposed to the threat of oil spills associated with the offshore and coastal activities. So this exposure requires the need for risk assessment, for oil spill trajectory modeling, for emergency response planning to kind of mitigate or minimize the potential impacts on coastal communities, on the marine ecosystems, fisheries, and other critical infrastructure. So it could be in different ways. So one way is during environmental impact assessments before operations even begin. These models could be used to simulate hypothetical spill scenarios under different ocean and weather conditions, considering seasonality, tidal states, waves, tropical storms passing, all those things. And the models could help predict where the oil could travel, which coastlines could be potentially affected, which environmentally sensitive area that could be, if it has an area, if that could be affected, and how quickly the impacts could occur. These results are usually used to develop management plans, contingency strategies, and other mitigation measures before drilling or production activities even begin. In some cases, these management plans are needed before these certificates and environmental clearances are even issued. And so that's being proactive. The other application is if there actually has an accidental spill event happening. Once the information is available on the spill location, time, the spill properties, oil spill properties, the forecast model could produce the trajectory predictions within about an hour. And we'll use that'll be used in the latest forecasted currents, winds, and wave conditions to estimate how the spill will move and spread over the next few hours to days. And this would allow emergency responders and whoever is responsible to prioritize areas for containment, to see which areas might be impacted, to be able to try to mitigate or protect the coastal areas. Like for example, on our East Coast, we have mangroves. We have some reefs in the northeast. And we have all throughout here, we have beaches that people use. So it is useful for in case anything happens. Another application, it's related to the oil and gas as well, which is the drill cuttings and mud dispersion. This is where cuttings and drilling muds are discharged during drilling operations below the sea surface, and this is discharged near to the water surface, will result in a rapid initial dispersion of the drill cuttings in the water column as it's released due to turbulence, due to currents, due to wave-driven mixing. And because the drill cuttings are denser than the surrounding seawater, it leads to sinking. So the plume sinks towards the seabed. It usually happens very quickly, but while this is happening, it spreads horizontally and vertically through the water column and results in mounds on the seabed close to the well and the rig. So it has it in this image here. So the models are able to simulate this during the environmental impact assessment stage for management plans to be developed. How are they going to minimize the drill cuttings discharge? How are they gonna monitor for recovery? So it's important for the plants to be developed as the benthic organisms living in the seafloor there are physically smothered with the discharge, and it will be stressed out. So these little critters, and it takes 1 to 2 years we've seen for the start of recovery and the recolonization of the benthic organisms in the water depths up to 200 meters. But generally the impact was like less than 1% of the block acreage. So it's a smallish area compared to the bigger ones, but it's still an impact. And during the post-drilling monitoring, side scan surveys are usually done to find the mounds. And it's been usually in the same predicted area that our models have done. And the affected areas are usually monitored for the benthic recovery through periodic sampling. In terms of management of marine ecosystems, we have used the models to explore the interaction between the ocean currents and the reef systems. This one is in Tobago, and what I mean is that, coral reef organisms tend to stay attached to the reefs as adults, but their larval stage is pelagic. So in the sense that it can be dispersed to other areas or reefs. This is crucial because it allows connectivity within and between reef systems for population replenishment, habitat colonization, and overall reef expansion. So the oceanographic factors, current velocity, temperature, salinity, waves, affect this dispersal of influences it and affects their viability and the natural receding of habitats. So to understand the area is important for coral management and restoration. In this case, the MIG 21/3 hydrodynamic model, coupled with an agent-based model, was used for the reef connectivity assessment in Tobago, and it was the HD model provided ocean conditions, while the agent-based modeling provided the factors such as settlement behavior, mortality, and other factors specific to the larval. And in this example, the dispersion can be seen from, this is Angel Reef to the northeast of Tobago, where it's dispersed broadly due to the stronger currents and deeper waters, reaching Grenada. And the other reefs that was modeled circulated closer to Tobago due to shallower waters and weaker currents. Another application is mangrove restoration. So numerical models we have been using it. In this case, is in Jamaica, where there were areas of mangrove dieback, and we were assessing what was the environment historically and present to kind of cause the degradation. In this case, it was determined that the area was fragmented due to a roadway construction as well as blocked drainage channels. So we've used the HD model to represent it, and we mimic the environment to see what was the hydraulic connectivity and what was the tidal flushing in area to evaluate, and that served as a baseline for us to evaluate potential restoration activities to improve the connectivity and flushing. So we tested out various scenarios to see which one would be the most effective to support the natural recovery of the mangroves. And if you could see here between this area, there was improved tidal flushing where the water moved in after the proposed solution. Water instead moved in phase with the elevations outside the area. So to summarize, we must represent the natural processes to predict how the environment works, how would projects even impact the environment, how we can represent what would happen. And numerical modeling offers a cost-effective way to address the situation where it can address how complex project requirements, and it could be tailored for projects as needed. Most of the global models we've used, the resolution is not enough as yet for our small islands, especially in the Eastern Caribbean. So we developed the higher resolution HD and spectral wave models to just improve on the resolution and to be able to generate accurate short-term forecasts, and while also understanding the mean currents and waves across the region. These larger models were developed with a balance of computational resources and accuracy, but there's ongoing refinements and child models developed as needed on a project basis. It has been used so far in a lot of applications, such as oil spill trajectories, drill cuttings dispersion, coral larval dispersion from reefs, and also potential mangrove restoration strategies. So thank you for your attention, and feel free to ask any questions or comments. And if you need to get in contact with us, I have the information there for Coastal. And if you want to get in contact with me specifically, I have the QR code here for my LinkedIn profile. That's it.
Thank you very much, Salomi. Very interesting and exhaustive presentation of application-oriented modeling and correct pathway to calibrate and validate. So we have two questions to start with, and then I have my own, but I would prefer to go with the public's question first. So the first one is, thanks for the presentation, and a curiosity, why was an agent-based model used for the coral larval dispersal and not a Lagrangian particle tracking approach?
If I recall, it was the best suited one to the hydrodynamic, and it incorporated more of the larval factors that we wanted to include. Yeah, but I can follow up if needed.
Yeah, that would be nice. So talking to Gloria Mozzi, I mean, she can get in touch with you and explore further the question. We have another question, is a great talk. Do you publish your flow fields as NetCDF for other users?
No. Well, no. We are as we are a private consultancy. It's our data is based on client subscription. Or as projects.
Yeah. Thank you. And then Dino Jerevchevich. I'm sorry, I shouldn't say it so much. You mentioned here there was a lot of gap in historical data. Can you give a bit more comment on this? What kind of meteorological stations or measurements do you have?
So it's in terms of the ocean measurements, it's a lot of, honestly, siloed or short-term deployments that are usually done for the waves and currents across Trinidad and Tobago. So it's not a consistent long-term location, and this is why the model is kind of used so we can always pull from wherever we want for a long period. In terms of the met stations, we have short-term ones that we have deployed from our projects or even within the company. They range from a few months to a year at different locations. But we also use whatever publicly we can get. So in Trinidad, we have a Met service agency that has a Met station at our Piñaco airport, which is inland. But that's inland. We also want winds along the coast to see how those work. So we have those as well that help validate what we measure, what we model. But generally the Met ones we pull from NOAA GFS or even sometimes mostly NOAA GFS. The ocean ones we pull from Copernicus.
Yeah, thank you. Yeah, this is a chronic issue that I do think that should be solved by public institutions, letting free and open data for private companies to develop such products like the one that Salomi has shown. But this is a long discussion, and I think that, I think hopefully we will evolve in that direction with operational oceanography and more data available open and free from public institutions. So that's my own opinion, but just gave my grain of salt. Then we have here another important question. Has a communication and/or training plan been developed for stakeholders to effectively use the model, I guess, output, particularly for groups such as fishers and emerging management officials who may not have an academic or technical background? This is a very relevant question. Thank you, Salomi.
So at this point, we don't have for community stakeholders to access, like community members or public members to access the model outputs. As I said earlier, it depends on the client. But based on the client, we have a easy to use dashboard or portal that they can see for their selected location. It wouldn't be just the whole 2D field, it will be points where they can see the actual wave height or current speed, whatever they need to view, along with whatever thresholds they require for their operations. So not as yet for a training plan.
Yeah, thank you. If I might add to this question that is extremely relevant, I think that this is the further step that we are undertaking in several activities in the UN decade, is enhancing the training capacity of modelers in general to give appropriate customized web platforms with availability of data translated into a language that is accessible. And the value chain is something that we are constructing the decade. So important is to have companies with us that already give their products, but they, again, they have to develop maybe more an interface, hopefully, that will allow what they think is possible to be accessed, or what is to be developed for commercial uses. So I think this is a very important topic, and it should be addressed at the level of the community, yes, a larger community, and find the standards at the level of IOC and the decade. So I hope, I hope we will. Yeah, please, Salomi.
Well, while we doing while the exact model outputs are not like from the forecast model itself, but within the EIA process, we do share the modeling results and everything with the community through stakeholder consultations, to make sure that we also learn from them how the area works, and we also communicate with them what their perception is, as well as how our science can show how the project would impact the area. So they are included in that regard.
So if I might ask myself a question now, Salomi, your modeling is impressive, so congratulations. We call it more a sub-regional modeling because of the vastity, the extension of your model domain. And here comes my concern, that is not concern, but question that is more on, if you have knowledge on the sensitivity of your domain size for the simulated currents, how sensitive these outputs are to the position of the boundary. I see that you have a larger domain for waves, which looks coherent. I mean, it's definitely, but for currents, I see some departure from observations. And have you thought of relating it to the size and of the domain?
I mean, ideally, we would expand the domain for the hydrodynamic model, but it's very computationally demanding, and so that's why the domain size we've chosen represents this. Yes, there's a few discrepancies, but there is a balance between the accuracy and the modeling. Depending on where we need, we will refine it to improve the accuracy. So it does improve resolution of the domain in those areas. But yeah, generally, yeah. But the waves, because that domain is so much larger, we can see the passage of the tropical cyclones in there.
Yeah. So we have another question by Christina Forbes, U.S. Coast Guard's excellent talk. Is your model data being used for search and rescue?
We have used it once or twice for search and rescue, or sometimes. I guess it depends on if it's search and recovery, but we haven't used it extensively for that. But we have done one or two trajectories.
Thank you. And so if we have no more questions on this very interesting approach and, real forward-looking way of starting to enter the disaster risk reduction arena from a private company point of view. I should thank again Salomi for being available and for giving us such a nice explanation of the potentialities and the things that are already done. And I hope to have you again, maybe in a few months' time, and show more. And again, have a good afternoon or evening or morning, everybody. Thank you.
Thank you. Thanks to CDL. We have an amazing team.
Bye.
Bye.